Alright, to start off, let's define concentration. The concentration of a solution is a measure of the amount of solute in a given quantity of solvent. This is where solute is the substance being dissolved, and where solvent is the substance doing the dissolving.
So for example, here the red molecules represent the sugar, the solute, whereas the surrounding area is the solvent, water.
So how do we distinguish between concentrations and dilutions? Basically, with dilutions, there's more solvent than solute, whereas for concentrations, it's the opposite, with more solute than solvent. Alright, so let's define our three types of concentrations. So our first definition is mass percentage, which is used to express the concentration of a solution when the mass of a solute and the mass of a solution is given. Now, volume percentage is used to express the concentration of a solution when the volume of a solute and the volume of a solution is given. In general, 1 part per million means 1 part of solute for every 10 to the power of 6 parts solution.
The universal solvent is water. Water is a polar molecule. That means that ionic solutions can dissolve in it. However, water is not the only solvent for ionic solutions. Any polar substance will also form an ion-dipole attraction. In the water molecule, the positive dipole in hydrogen is attracted to the anions on the surface of the solid ionic compound, while the negative dipole is attracted towards the cations, forming an ion-dipole attraction. All these attractions have a "come on, baby" attraction. So our first sample calculation is calculate the concentration of an 825 milliliter solution that contains 30 grams of acetic acid. So the first step is to convert the amount of grams to moles using the mass over molar mass equation. Next, we use the concentration equation, C equals N over V, where N is the amount of moles and V is volume in liters, and C the concentration measured by molarity, which is the units of moles per liter. So our next sample question is, if 25 milliliters of sodium nitrate solution is added to sodium carbonate solution, what is the concentration of the sodium cations in the resulting solution? For these two solutions, when added together, the final volume will be 35 milliliters. Next, we can see that for the sodium nitrate solution, there's only one sodium ion per molecule, which means the moles of sodium ion will be equivalent to moles of sodium nitrate. For the sodium carbonate solution, we can see that there are 2 sodium ions per carbonate ion. This means that the moles of sodium ions will be double the moles of sodium carbonate. So as concentration is directly proportional to moles, we can double the molarity of the solution to find the concentration of sodium ions. We can then find the mole values by using the rearranged formula of C equals N over V. Then, we add the mole values together as they are combined in the final solution. Finally, to find the concentration of the sodium ions, we can use our C equals N over V equation once again with our newly found mole values and the final volume of 35 milliliters.
So our next question is, which of the following contains the greatest amount of chloride anions? A. 200 milliliters of 0.25 molar hydrochloric acid, or B. 500 milliliters of 0.5 molar magnesium chloride. So to find which solution has the greatest amount of chloride anions, we have to find the number of chloride ions in each solution, then compare our answers. So for both sets of information, we use the N equals CV formula to find the number of moles in each solution. Be sure to convert milliliters to liters. Since there is only one chloride ion per hydrochloric acid molecule, there are the same number of chloride ions as hydrochloric acid molecules. But since there are 2 chloride ions for every molecule of magnesium chloride, we have to multiply the number of magnesium chloride molecules by 2 to get the number of chloride ions in that solution. So, we know that there's more chloride anions in the hydrochloric acid solution. Moving on to our next question, let's calculate the mass of nickel 2 sulfate contained in 200 grams of a 6% aqueous solution. So in order to calculate for mass percentage, we divide the mass of the solute by the mass of the solution and multiply by 100. Now here, the 6% aqueous solution means that 6 grams of nickel 2 sulfate are present in 100 grams of solution. Our variable x represents the mass in grams of nickel 2 sulfate that we need to find in this particular solution. Now we just isolate for x. And the grams of solution unit cancels out, leaving us with 12 grams of nickel 2 sulfate. Next up, rubbing alcohol is commonly used as an antiseptic for small cuts. It is sold as 70% solution of isopropyl alcohol in water. So what volume of isopropyl alcohol is used to make 500 milliliters of rubbing alcohol? So the volume percentage equation is very similar to the mass one in that it is the exact same except we're calculating for volume. So we know that the volume percentage and the volume of the solution. So therefore, X represents the volume of the isopropyl alcohol we need to calculate. Next, we rearrange the equation to isolate for X, and then the milliliters will cancel out, which in turn will give us the final answer of 350 milliliters of isopropyl alcohol needed to make 500 milliliters of rubbing alcohol. The final question is, what is the concentration in parts per million of bromide ions of a solution from which 0.1304 grams of aluminum bromide was dissolved in 850 milliliters of water? So how do we use part per million or part per billion? 1 part per million is equal to 1 part solute for every 1 million parts of solvent. Thus, 1 part per billion is equal to 1 part solute for every 1 billion parts of solvent. In aqueous solutions, a concentration of 1 part per million is equal to 1 milligram of solute per 1 kilogram of solution. This is because 1 milligram and 1 kilogram have a difference of 10 to the power of 6, or 1 million, which is why 1 milligram per kilogram is equal to 1 part per million. The same can be said for 1 part per billion. 1 part per billion is 1 microgram of solute per 1 kilogram of solvent. 1 microgram and 1 kilogram have a difference of 10 to the power of 9, or 1 billion, thus making it 1 part per billion. Since 1 kilogram of water at 4 degrees Celsius and at standard atmospheric pressure, or 101.3 kilopascals, is exactly 1 liter, we can see that 1 part per million is equal to 1 milligram of solute per 1 liter of water. Similarly, 1 part per billion is equal to 1 microgram of solute per 1 liter of solution. So to solve the problem, we're going to use the equation of part per million is equal to mass of solute times 10 to the power of 6 divided by mass of solvent. So we have to find the unknowns in this equation. The first unknown of the equation is the mass of the solute. To do this, we use the equation of number of moles of aluminum bromide is equal to the mass over the molar mass. By substituting in the givens of the problem, we arrive at the number of moles of aluminum bromide. However, since there are 3 bromide ions per molecule of aluminum bromide, we have to multiply the number of moles of aluminum bromide by 3 to get the number of bromide ions. Finally, to convert back to the mass, we multiply the number of moles of bromide ions by the molar mass of bromide to get 0.1172 grams of bromide ions. So note that there's actually a mistake in the video, and there's actually 0.117721 grams of bromide and not 0.00146669 like it's shown in the video. Our next unknown is the mass of the solvent. So to get the total mass of the solvent, make sure that you add the mass of the solute to the mass of the solvent to get the total mass and not just the mass of the water. Now that we have all of our unknowns, we can finally solve for the concentration of the solution. So therefore, the concentration of bromide ions in this solution to 3 sig figs is 138 parts per million.
I still have to write my script and record it. Everybody get to work now.